Thank you. So this is a work done in collaboration with Aurélien Grabsch, which is who is another PhD student, Satya Majumdar, who is here, and Gregory Scher. So at first I will introduce the problem by some reminder of extreme value statistics for i.i.d. random variable. I'm sure that all of you know about it, but still. Then I will consider the case of matrices of real eigenvalues and matrices of complex eigenvalues. Therefore, this talk will have some overlap with the lectures done by Satya last week. Okay. So first, when we consider a large number n of i.i.d. random variable, we know that there is 3 classes of universality that depends on the tail of the individual distribution P of x. So if P of x decreases faster than any power law, then we obtain with some rescaling a typical distribution given by a Gumbel law. If it decreases like a power law, then we know that in the large n limit we have a Fréchet law. And if it has some finite edge at which it decreases as such, then we obtain a Weibull law, which is described here. So these two are true for x positive. Okay. Now let us come to another example, which is the case of random matrix theory. So if we take a matrix composed by random variables which are Gaussian as such, and they are complex for the upper part, and the matrix is Hermitian, then the probability weight for this matrix is given as such. And because there is a trace, you can see that it will depend only on the eigenvalues of the matrix. And then we can separate between eigenvalues and eigenvector to obtain the joint PDF of eigenvalues, and we obtain this expression. You can see here that this can be interpreted as particles confined by a harmonic potential and that are interacting with a 2D logarithmic Coulomb repulsion. So the variables are now identically distributed, but they are correlated. If we compute the average density for this kind of eigenvalue, we obtain a semicircle law as such. And so we can guess that the largest eigenvalue lambda max will tend to square root 2 as n tends to infinity. We can also obtain the typical fluctuation by doing this integral, and we found out that they are peaked around square root 2 with a typical fluctuation of order n to the minus 2/3. Now, the typical distribution has been worked out for this kind of problem by Tracy and Widom in 1994. And in this typical regime, you have a limiting distribution given by the Tracy-Widom distribution of index 2. So this index corresponds to the symmetries of the matrix, which is Hermitian in our case. And you can also compute the asymptotic tails of this distribution, and you see that it is highly non-symmetric. It is highly more decreasing on this part than on the other part. Okay. And so for this problem, we can also compute the large deviation functions. And there is a nice review about it done by Majumdar and Scher. And you can actually work out the form of this function. And when you compute the limits, for when x tends to square root 2 on the upper part or the lower part, you see that there is a nice smooth matching with the typical regime. Now, how to obtain this large deviation function? You can start from the energy that depends on the actual position of all the eigenvalues, and then you see that if you want to have the largest eigenvalue, which is lower than square root 2, you need to push all the charges. So in this case, the cost will be proportional to n to the power 2, and you will have a different average distribution. Whereas if you want the rightmost charge to be larger than square root 2, you only need to take one eigenvalue from the distribution and make it go to right position, and the cost will be of order n. Now, to evaluate the left large deviation, you can go from this energy to a functional energy that depends on the distribution and on the position of the rightmost part. And so you see that you have this potential term, you have this interaction term, and you have this constraint that is given with a Lagrange multiplier. Then you can minimize the functional with respect to the distribution, and you obtain this nice formula. And by resolving it, you can actually compute the distribution in this case, and then the large deviation function is just the difference between this energy and the energy at equilibrium. Okay. Now, for the right large deviation function, you only need to pull one charge from the bulk of charges, and you can compute its energy within the bulk and out of the bulk, and the large deviation function will be just the difference between these two quantities. Now, as we've seen, the distribution of eigenvalue is given by this formula. So you have one part which is the energy, which is lambda I to the power square, and then you have n, and then there is the logarithmic repulsion. Okay. And so what you can do actually to change this distribution, you have many possibilities. So first, you can change the potential term here. And as we've seen from Satya's lecture, as long as the density decreases like a square root for next to lambda max, then you will always have the typical distribution given by the Tracy-Widom distribution. But the large deviation will be different. Now, you can change also the inverse temperature that appears here, and this will just change the typical distribution, but the large deviation are the same. Now, another thing that you can do is changing the interaction, as it was done, for example, in the talk by Anupam last week. So using the actual one-dimensional Coulomb repulsion, and you see that in this case everything will be different. So both the typical regime and the large deviation will be different. And the last thing we can do is change the dimension. So here our eigenvalues were living in a one-dimensional space. So you had this well, and you had a repulsion between charges. But you can go to higher dimension, and this is what we will focus on for the rest of the talk. So now if you take a matrix, but you do not impose any constraint on the variables within, there are just Gaussians that are complex Gaussians, and you renormalize by a factor 1 over square root 10, and then you can compute the PDF of complex eigenvalues, and you see that in fact you obtain the same joint PDF as we had before, that is written here. The only difference being that now our eigenvalues zk live in a two-dimensional space. Okay? And you can compute for this new problem the density, the average density in the large n limit, and what you obtain is the Gaussian law. So basically you have an homogeneous distribution of charges within the bulk, within the unit disk, and outside this disk you have in the large n limit no eigenvalues. So that means that for the extreme value statistics, the largest radius will tend to 1 in the large n limit. Okay. Now we want to compute what is the behavior of the cumulative distribution function Qn of W. And to do such, it was done by Ryder in 2003, and he proved actually that in the typical regime you have a Gumbel distribution as for i.i.d. random variable. So this is quite surprising because as we've seen, the eigenvalues are now clearly correlated. And you can also compute the large deviation functions, and it was done by Kunden et al. And you obtain these large deviation function at the left that goes like n square with rapidity n square, and at the left with rapidity n. So this is basically the same as for the GUE case. And these rate functions are given as such. So as I said, to obtain this function, you can still use this method of function. Okay. Now we can check, for example, the right matching. And from the inside, we know that the Gumbel distribution will behave for x goes to infinity as an exponential. And using the expression for the coefficient, we find this form. Now, from the outside part, it is a bit tricky because the edge is in 1. So you have this. So you have 1 here. Here you have the left large deviation. You have the Gumbel distribution, which is around something that is a bit more than 1. And then you have the left large deviation, which is here. And so here you have 1. So you need to use the small rescaling, And that way you obtain that the first derivative is non-zero in this position, and you obtain that there is indeed a smooth matching between the two. Now, for the left matching, you see now that the Gumbel distribution is this form. And if you take the left large deviation, you can see actually that when W goes to 1, you have a cubic power that goes on. So clearly here there is no matching between the two, so the typical regime and the left large deviation. So here there is a problem and we want to solve this problem. Now, this problem is very much related to the 2D one-component plasma, which is a gas of 2D charged particles of same charge that interact through this 2D Coulomb repulsion and that are confined in an external symmetric potential. And you see that the energy of such a gas will be of this form. And if you take V that is quadratic, then you obtain exactly what we had for this Ginibre case. And so you can use a complex representation for the position of the charges, and this gives exactly Ginibre. So now let me come to the results. We have found that there is actually an intermediate deviation regime that allows a smooth matching between the typical regime given by the Ginibre case, by the Gumbel law, and the left large deviation, and the intermediate weight function is given as such. Now, another big statement is that this intermediate deviation is universal for all symmetric potential, given the fact that the potential is great with respect to log r for r to infinity. And in this case, you can work out the edge of the density and the typical scale of variation around this thing. Okay. So a thing that I did not mention was that for the so Ryder actually proved that this Gumbel law is also universal for this type of potential, and Kunden et al. Proved that it was also the case for the large deviations. So now, how to derive these results? Actually, we can introduce orthogonal polynomials that are just power law with respect to z. And if we compute this quantity, you see that indeed there is a Kronecker delta. So these polynomials are indeed orthogonal with respect to this weight function. Now, if we compute the following quantity, which is 2 times the determinant of this quantity times the Gaussian part, then you obtain that this gives exactly the joint distribution. Indeed, when you have these polynomials, you compute the determinant of polynomials, you obtain this Vandermonde determinant here. And now we can use a very important theorem that is the following, which is the Cauchy-Binet-Andreev theorem. So when you have a determinant of Fi xj, determinant of H L x m, and product on K of J xk, then this is given by n factorial times the determinant. So these determinants are all of size n. And this gives the determinant of the integral of dx f I of x h L of x times g of x. And now, if we use, for instance, as g an indicator function, we can prove that the cumulative distribution function can be computed with this nice property, and we can prove then that it is given as the product of individual cumulative distribution of some random variable xk that are no independent, but they are non-identically distributed. So this gives some insight of why this Gumbel distribution has shown up in the typical regime. Now we want to know where to look at for this to obtain this intermediate rate function, and to do such we can compute the average density at finite n, and it has this nice form. So we know that for infinite n it tends to the Gekko's law, and for large but finite n actually we can see that there is a nice scaling function here that allows to go from the non-zero value to the zero value on a typical size of order 1 over square root n. And actually we can see that this regime matches exactly the regime that we wanted to investigate. So this is the regime that we will study here. Now, this individual cumulative distribution function can be put as such by setting u equal k over n, and then when we have these formulas, we can use a saddle point approximation to get this CDF. So we can see that actually there is two cases. So first, we integrate up to W. The first case is that this function phi u has its minimum within the interval of integration, and it gives this nice form. But if now the minimum is outside of the interval of integration, it gives this form. And so with that, we can compute actually the full CDF, which is just the product up to n of these individual CDF. And we can see that there is a first part given by this, and then there is a second part that I did not put in all, but that is as such. And so you can see that when W goes to 1, this second part here is behaves nicely, and it actually vanishes. And when introducing this rescaled variable p, you can see that you can actually compute this intermediate rate function, which is given as such. And now that we obtain it, we want to check if the matching is good now. So we can use the property of the complementary elf function, And we can find that actually phi I goes to this nice form for y goes to plus infinity. And using this rescaling to obtain a matching with the typical distribution, we can see that here there is indeed a nice Gumbel form that is coming out of the computation. And we can retrieve the exact form of this CN. Now, for the matching that posed also a problem with the left deviation, which is cubic, you can see that if we take this form and you replace it in the computation, you obtain a power cube that will nicely match from the inside part the left large deviation, which is on the outside part. So now we have a clear picture where all these four regimes match smoothly with each other. And you can see that actually there is this intermediate regime that is present on a very narrow region and that we could not access with the previous method. And now, for the universality of such a computation, we have seen that if V of R is large compared to log R, actually there is always a finite edge, R edge, at which the density drops from a non-zero value to a zero value. The typical regime is still Gumbel, as was proved by Ryder. The left large deviation rate function vanishes as a power cube. This was proved by Kunden et al. And these polynomials are still orthogonal with respect to this measure. And you can see that it is a bit more complicated, but still we can do much of work with this. And so we can, indeed, we can use the same saddle point approximation for all potential V of R that grows faster than log of R. And you can see actually here why this property of log of R is relevant. And so with all these properties, we can see that this intermediate rate function phi1 is universal with respect to the potential V of R under such condition. So now let me conclude. We found a universal intermediate deviation regime that solved a puzzle in the matching of typical regimes and large deviations. So actually, it was known that this form could actually appear, but most of the time people used it as just as an intermediate step to get the Gumbel distribution. And now we see that actually it has relevance because it allows to have a smooth matching with this left large deviation. And all these four regimes now match smoothly. And actually, a similar result was obtained before by a previous work that we did for fermions in a hard box. And Gregory will give a talk tomorrow about this subject. And there is a paper on the archive. Now, a question is, as we've seen, we considered the case where these qk of W goes when W goes to infinity as is great to respect to any power law, which correspond to the Gumbel case. Okay, but now what happens if we consider other types of distribution? For example, if we consider a PDF, a joint PDF with a large tail, actually, we can see that if we use this kind of thing, we have for alpha equal 1, this is actually related to another problem of random matrices, which is the case when A and B are Ginibre matrices, and you want to compute the eigenvalue of M, which is A minus 1 times B. And now the distribution of Z1 Zn is given with also this logarithmic repulsion between charges, Zi minus Zj to the power square. And we have this type of distribution, 1 plus Zk square to the square, and you can see that here we have a large tail. And actually we found that, for instance, in this case, the typical distribution is not given by Frechet law, as it is the case for i.i.d. random variables. And another interesting thing to do is to consider the joint PDF with a hard edge. And this can also be done when you consider a unitary matrix, U, and you take it as a block form, A, B, C, D. Okay, U is of size M times M, and A is of size N times N. Then if you consider the eigenvalues of A, you can see that actually it is given as the joint probability distribution function for such eigenvalue is given as P. So you still have this repulsion, Zi minus Zj to the square, and then you have this weight, which is 1 minus Zi to the square to the power nu, with nu, which is given by M minus N minus 1, I think. And so you can see that in this case, the distribution in the typical regime is given now by Weibull law as for i.i.d. random variables, but you still have this interesting intermediate rate function. And so with this, I would like to thank the organizers, and that's it. Thank you.
Any questions?
Sorry?
Beta?
Quantum 1 to the power beta?
With a probability beta. Actually, so if you put beta here, it's more complicated because you don't have these nice determinantal properties. And so we didn't manage yet to do any calculation about this thing. We only consider the case of beta equal to.
So this, this orthogonal polynomials that you find, I mean, so can one still write it as some like, so do this correspond to eigenstates of some quantum Hamiltonian?
Sorry?
The orthogonal polynomials that you get,
yes.
Do they correspond to eigenstates of some?
Yes, exactly. So if you consider the case of fermions that are charged in a magnetic field, and you consider a symmetric gauge, then if you compute the distribution of these fermions in the lowest Landau level, then you obtain exactly these polynomials. Yes. So here again, there is a nice connection between random matrix theory and these problems of fermions without interaction.
Question, if I may. In the one-dimensional case, you have this nice picture with the density in order to find a large deviation, like change on the density to get above or below the square root 2. In 2D, can you do also this kind of analysis to how do I have to change the cloud of charges?
Actually, you can do it, and it's much more simple in this case. So let me show it to you. So you have actually a nice property which is given by the fact that we have this Coulomb repulsion that is present here, which is exactly the one of 2D, and this is 2D. So if you compute the energy with respect to rho, then you have this first term that is dz bar rho of z, v of z, of modulus of z. And then you have minus double integral dz bar dz prime bar rho of z prime log of z minus z prime. Then when you do the functional derivative of this, then you obtain just 0, which is equal to v of modulus of z minus 2 integral dz prime bar rho of z prime log of z minus z prime. Then you can use actually that this log function is the Green's function for the Laplace operator, and then you can prove that this density here is expressed so for potential which is symmetric as 1 over 4 pi r d over dr of r v prime of r. Okay, so this is much simple. And when you add a wall, actually, what is going on is that charges tend to accumulate at the position of the wall, and you just add a Dirac delta function to this, and you can compute things very easily.
Any questions? If not, let's thank Bertrand again.